Hello, everyone. My name is Scott Grizzard. This is Calculus 1, Fall 2020. I'm from the University of South Florida. And tonight we're going to be talking about optimization 2. So I need to put a little disclaimer on this. What we want to do is we kind of want to, what I want to do tonight, and what I want you guys to do is we're going to try and tie up this section in a little bow. So what we're going to do is we're going to math our way through some of these econ problem type things and show that this technique, and there's kind of two things I could do. I could do kind of economics type things, or I could do like statistics types things, because this is also ties into statistics. I'm going to do econ. I think it's more fun and interesting, and the examples are kind of more intuitive. But what we're going to talk about is kind of an alternative approach to optimization. And then we're going to kind of try to tie everything together with the intuition about the first and second derivatives. Now, I need to preface this with the following disclaimer. Okay. This is not so much the technique we're going to use is extremely useful, but you can get away with not using this technique. So you can get away, if you want to, with just using regular optimization, and that's fine on the test. So do you need this information for the test? You don't need this technique for the test. You can get away without it. But it does kind of bring the intuition together. So if you don't like the technique and you don't want to do it, that's fine. But I encourage you to watch the video and try to take notes and all of those things. One, the notes are required anyway. But two, because if you look at this, there's a deep insight into the nature of these problems, and kind of a deep insight into the connection between calculus and the real world, and how we model things in economics, statistics, sciences, all those things. So that's what I'm encouraging you to do tonight. Even if you don't like the technique, just kind of go for it and kind of zen out. And this technique, by the way, is in your book. And there's a question, can you use this technique if you like it better? Absolutely. You can use this technique if you like it better on the test. It is in your textbook, but it's kind of buried. And he brings it back later in the book. So if you go to Calc 3, you'll see it there. You'll definitely see it in Calc 3. But this is one of those things that he kind of buries. It's a note. It's one of those things, it looked like he wanted to say more about this. And then the people that were, editing the textbook were like, no, if you say this, only like fewer people will adopt your book and stuff like that. So you can't do that. Okay. But it's, if you look in the book, let me see if I can find the page. It's note 2 in section 4.5. After the first derivative test for absolute extreme values, if you look underneath it there, you'll see this thing called alternative method for solving optimization problems. So that's what I'm doing tonight. And then I'm talking about the insight that we can get from the second derivative and things like that. Okay, so that's the plan. And yes, you can absolutely use this on the test if you'd like it better. I'd like it better, but especially for certain problems, it works a lot faster. For maximization problems, it's not all that great speed-wise, but for minimization problems, it's a lot faster. So this is how it works. Here's the big idea. So here's the problem we're going to use as our example. The Acme Corporation produces jet-propelled pogo sticks according to the following Cobb Douglas means that these things, that it's don't worry about that word yet. You can look up that word if you want to on the internet, but we'll talk about that later. Cobb Douglas production function. So I've got some output level, and I've got the skilled workers and unskilled workers. Okay. So the idea is I have a bunch of machines. I have some union labor. And they're highly skilled, but they cost more money. Whereas I also have unskilled labor. So there are certain tasks that I can give to unskilled labor that they'll do, and there's certain things I really need skilled workers for. But I can substitute them for each other on the margin a little bit, right? So if I'm okay with the fact that I can have the expensive computer technician also sweep the floor. Okay. But it's not really, he's got a lot of skills, and it may not be the best use of his time. Whereas I could get people that don't know what they're doing to try and be computer technicians, I suppose. But they're not going to be very good at it. And it's going to cost me a lot of money in, them trying to figure out what to do. It's kind of the idea. Now, that seems a little cold and crass, and what do you want? It's an economics problem. So be cold and crass for a minute. But I'm looking at this, and I want to produce 1,000 jet-propelled pogo sticks per week. All right? So if this is my production function, what's kind of the optimal allocation, right? How many hours of unskilled labor do I want, and how many hours of skilled labor do I want? So 1 to 5, how do we feel about this setup? What the kind of questions going? I've got 2 resources. Capital and labor are also a common way this thing is set up. I just set it up skilled and unskilled. So do I have a 1 to 5er tonight? Maybe not. Oh, I do. Cool beans. And 1 poll is not up. Okay. So that's kind of the setup here. So here's what I'm going to do. Now, traditionally what I would do, the beginning's kind of the same, right? So I've got output, I've got a production function. Here I'm actually producing output, but it could be area or whatever. But here I've got a function that's Q equals S to the 1/2 L to the 1/2. And then I have a cost function, and my cost function is, it's going to cost me the $9 I paid to the skilled labor, so the unskilled labor. So it's going to cost me 9L plus 36 times S. Okay? And I know I want my output here. I want my output, this is fixed at 1,000. And this right here is minimize. So I want to minimize my cost given the production of 1,000. Okay? Now, normally what I would do is I'd solve for one of these variables. Right? So the other way, the normal way, or the first way, solve for L or Q, and then plug into C to get an equation with one unknown. And I know my face is over that. Okay? So that would be the normal way to do that. So 1 to 5, how do we kind of feel about that? Let me turn off the camera. There we go. That would be the normal way, right? I'd take 1,000 equals S to the 1/2, L to the 1/2, which would give me 1,000 over S. This would be squared equals L, which would give me, when I combined it with the other one, it gives me that 9 times 1,000 squared over 5 over S plus 36S equals C. And then I take the derivative and I solve for 0. I get one equation, one unknown. Okay. Or 2 unknowns, depending on how you cut the C. But let me ask you this. If I take the derivative with respect to cost, what I'm going to do is I'm just going to take the derivative of everything. I'm going to pick one of the variables, okay? So I'm just going to say here, let's see, which one's going to give me better math? They're all kind of big. I'm going to say let L drive. Okay? So what I'm going to do is I'm going to do dc, I'm going to do dq over dl. Now, so I've got s moves, q fixed, c optimized. All right, so L's driving, S moves, Q's fixed, and C's optimized. So what I'm going to do is I'm going to take the derivative with respect to L of this. Now this S moves with L. Okay? So since S moves with L, I'm going to have a product rule here. So I'm going to have the derivative of the first times the second plus the first times the derivative of the second. Right? And I'm going to take the product rule here. So I'm going to take the product rule here, and I'm going to get, so I did the product rule. This has a chain. So this is going to be 1/2 S to the negative 1 over 2 ds over dl times L to the 1 over 2 plus S to the 1 over 2 times 1/2 L to the negative 1 over 2. Okay. So 1 to 5, how do we feel about that derivative there? All right. Now I'm going to do the same thing to cost. And what I'm going to get, I'm letting L drive, so this is going to be 9 plus 36 times ds over dl. Okay? Now, how do we feel about that one? No, good about that? Just 1 to 5 real fast. How do we feel about that one? Okay. Now, here's the trick. Here's the big insight, okay? Since C is fixed, dc over dl equals what? I'm sorry, since Q is fixed, dq over dl equals what? If Q is fixed, the derivative of Q with respect to L equals 0. Since C is optimized, dc over dl is set to 0. Now, does it matter which one is fixed and which one is optimized for the calculations? Right? Remember on the problem set today, I had this situation where what I was doing was I was solving, right? I was solving for this idea, was I fixed C, and then I solved for this. But does it matter which one is fixed? Right? When I calculated the expansion path today in the problem set, right? It didn't matter. I fixed C and I did the derivative for A. Right? I optimized A fixing C. But did it really matter? Could I have fixed A and minimized C and gotten the exact same equation? And the answer is yes. It doesn't matter. And that's the deep insight. So the minimizations of C, that's kind of a, that the math is less pleasant, right? Because I've got these, negative 2's and, the math is a little bit less pleasant when you're doing the minimum. But the point is, you can always do this. It doesn't matter whether you're maximizing or minimizing. You can actually do the exact same steps to get the result. Because the derivative with respect to Q if Q is fixed and C is optimized, dQ over dL is going to be 0, and dC over dL is going to be 0. If Q is optimized and C is fixed, dQ over dL equals 0, and dC over L equals 0. So 1 to 5, how do we feel about that? They're actually the same problem. And so there's this idea that I can get a little clever with it. Okay? If C is fixed, then I'm in good, if C is fixed, then its derivative is 0 because it's a constant. If Q is fixed, its derivative is 0 because it's a constant. If C is being optimized, well, its derivative is 0 because I'm looking for a min or a max. If Q is the thing being optimized, well, its derivative is 0 because I'm looking for a min or a max. So the point is, it just doesn't matter. I can do the same method to solve for either one. So what I've done here is I set both of these equal to 0. And now what I'm going to do is I'm going to solve for, in one of them, pick one, I'm going to solve for ds over dl. Okay, we can actually do it for both. So from this equation here, I get that, not that equation, this equation. From this thing right here, I get the following. I get that 1/2 s to the negative 1 over 2 ds over dl times l to the 1/2 plus s to the 1/2 times 1/2 l to the negative 1 over 2 equals 0. So now what I'm going to do is I'm going to solve for ds over dl. So I'm going to move everything on this side over here. So I got ds over dl equals, I'm going to take everything that was here, I'm going to stick it over here. Over, and then when I combine these things and then I divide over, this stuff here goes on the bottom. Now, when I do that, the 1/2's cancel. And notice here, the s here is on the bottom with a negative exponent. I'll move that to the top, and I'll move this one to the bottom. So what I'm going to get is s to the 1/2 times s to the 1/2 with a negative sign in front over l to the 1/2 times l to the 1/2. I add the exponents together, I get negative s over l. So now I have this equation here. Gives me the following. It gives me that 9 plus 36 ds over dl equals 0. And that gives me the following little bit here. That gives me ds over dl equals, so I move this over there, negative 9, and then I'm going to divide by the 36. And that gives me, brain, negative 1 over 4. So how do we feel about that, 1 to 5? What I've done is I've solved both for dl over dx. For ds over dl, I'm sorry. How do we feel about that? Now what I'm going to do is I'm just going to set them equal to each other. And look what pops out. I get negative 1 over 4 equals negative s over L, which implies that s over L equals 1 over 4. So what does that mean? So this means right now that when optimized, so I get this idea that I can actually solve for a ratio. Now, notice here that the terms for C and S just disappear. I get a ratio. And that happens here because this function is really nice. Okay? This function is S times L with some things up here. And these are called Cobb-Douglas. Okay? So the idea is that a Cobb-Douglas function is something like this. Okay, this is what a Cobb-Douglas function is. F is Cobb-Douglas if f of x equals x to the alpha. I need two variables. So the input, f is Cobb-Douglas if, so Cobb-Douglas. So I want f to go from R cross R to R, or some subsets of these, right? I can have functions that are positive only. So if I take a, b, I don't want to use a, b. Let's use x and y. Why not? So notice that z is now the output. If equals x to the alpha, y to the beta for constants alpha and beta. And you don't need to know that definition, but that's what the definition is. Okay? So the idea is that I've got a function here that's a function of two variables, where it's x to the alpha, y to the beta, or some variation on that theme. Okay? Now, these Cobb-Douglas production functions, and area is one, are nice. They've got some really nice features. One of them is that the ratio between skilled and the ratio between x and y is fixed. Okay? So 1 to 5, how do we feel about the fact that I now have a fixed ratio? I don't care what the optimization is. I don't care what the budget is. And I don't care how much output I want to produce. The ratio between skilled and unskilled labor that I want to employ doesn't depend on the level of output. In this case, in cases where the thing is, where your production function is Cobb-Douglas and your costs are linear. I just wind up with a ratio that I want. I want 1 to 4. I want one skilled worker for every one skilled hour of labor for every 4 unskilled hours of labor. Nobody's voting. Okay. Now, sometimes your C and your Q can wind up in these equations. Okay? Or you could have things like S squared here, which means that C or Q are going to wind up in your equations. But this is actually kind of cool. Because now I can do something very nice. Now I solve for one of these, and I have that, let's do S. So I have that S equals L over 4. Okay? When optimize. So now what I can do is I can go back and sub in back to my thing. So I had Q equaled S to the 1/2, L to the 1/2. Right? Equaled, and then my optimization was 1,000. So now what I do is I sub in L over 4, and I get S to the 1/2. So I can combine these two facts, and I get S to the 1/2. Not S to the 1/2. I want to replace that. I get L to the 1/2 over 2, because that's 4 to the 1/2, times L to the 1/2 equals 1,000. And that means that L equaled 500. Now with that, I sub in back here and I go, okay, well, if L is 500, that means S equals 500 over 4 equals brain 125. How do we feel about that? 1 to 5. Okay. Now that's nice, right? That gives me these things. Right? I need to check. So I could do a couple different things to check for my second derivative. Or I could do a couple of things to check for my max. But what I'm going to do is I'm just going to do the easy one. I'm going to cop out here. Instead of doing the double derivative of one of them and then solving, because that's kind of a pain in the neck. I could. I mean, it's not much of a big deal, right? If I wanted to do the double derivative of this, it's going to wind up being 36 d squared, times the derivative of this again. Okay? So that'll give me my double derivative. And then I get the sign of that thing. I can do that. But there's an easier way to do this now. Right? So this kind of thing, I've got endpoints and it looks like this. So I've got it's easier to just make an endpoint argument. The first or second derivative. I can do a first derivative test. The first derivative test is easier. Okay, so let's do the first derivative test then. So first derivative test. If we want to do that. Okay. So let's do the first derivative test. My derivative here is dc over dl equals 9 plus 36 times ds over dl. Correct? Now, what I need to know is what I do is I now take this thing here and I look at this other equation here. And I've got this thing right here. So how do you feel about this? 1 to 5. That was my first derivative of dc. Okay. Now what I'm going to do is I'm going to take this bit here, and I'm going to take my combined equation. So I wind up here. Let me see how would I do this. How did I do this before? Give me just a moment. It'll come to me. You asked a question that I should have been prepared for, and I'm not. And then I know that ds over dl. No, that's too complicated. Oh, here it is. And I know that ds over dl equals negative s over l. Right? That comes from this fact right here. Yes, because Q was fixed, so this is fixed, right? Work out the first derivative of the cost function. Oh, the cost function was 9L plus 36S, okay? So I take the derivative of that in terms of L, and I get 9 plus 36, right? The derivative with respect to S from the chain rule, okay? The derivative with respect to S from the chain rule here, I wind up with, right, so if I wanted to work this out, let me just do it here. So so the derivative with respect to L of the cost equation was 9L plus 36S. Right, and then I'm going to get 9, that's that bit, plus d over dl 36S. Now this is an S, that's an L, so I got to use the chain rule. So I do a little chain here, and I get 9 plus the 36 just comes out, the 36, and this, I should do d over ds of S times d over d L of S. And of course, this bit is 1. So I wind up with what's left, 9 plus 36 ds over dl. Was that the thing you were asking for? Okay. So if I want to do the first derivative test here, I use this thing right here. So dc over dl equals 9 plus 36 negative s over l. So that's going to be 9 minus 36 s over l. So now what I do is I pick a ratio that's slightly off. Okay? Does that make sense? Yes or no? So now I test ratios that are slightly off. If you want to do it this way. So I can do it this way, and I wind up with d. So this was where was my ratio? S over L was 1/4. So if I do dc over dl of 9 minus 36, let's see, if the top's bigger than the bottom, so if I did 1/5 as my ratio, when S to L equals 1/5, I do this, I'm going to wind up with a, because I'm less than 1/4, I wind up with a negative number. And then when I do dc over dl, when S over L equals 1/3, I'm going to wind up with a positive number. Do I have that backwards? Oh, this should be greater than 0. I'm sorry. 1/5 is... Hello, Scott. 1/5 is less than 1/4. Thank you. So I'm subtracting by something less here. I'm subtracting by something greater there. And I wind up with this, that and that there. Other way around. Let's see. So this is the cost. And which one's on the bottom? Nope. Here I made L bigger. So here L was bigger. Here L smaller. So this is like that, minus plus. So I have a min. Okay. That is not the way to do this because it's very confusing. The easier way to do this is just to make the endpoint argument. Since you asked me the question, you asked me actually a different question. So what I'm going to do here is I'm going to make the endpoint argument because it's actually easier. Now, the endpoints are L equals infinity and S equals infinity. So I found the minimum. Okay. That's just much easier. Isn't that easier? 1 to 5, how do we feel about the fact that that's being easier? It's not your fault. I misunderstood your question. I can do this. This is a valid first derivative test. It's annoying and a pain in the neck, but it's valid. Okay, I could also do a second derivative test, which would be equally big. Well, it's actually a little bit less of a pain in the neck. Because what I have is the exact same thing, and I just take the second derivative. So if I wanted to do a second derivative, right, I take dc over dl equals... Now remember, this first one was caused by the fact that it was fixed. So what I now need is d squared c over dl squared. So I'm going to take the derivative of this, and I'm going to have to use the quotient rule on this. I hate the quotient rule. So I wind up with, I mean, you can already see it's going to be negative, but I'll do it anyway. So this thing goes away. You wind up with 36 times, here's S, so this is going to be, I'm just going to do 36 times the whole thing. So the first, and I'm going to pull out that negative. So the top here is ds over dl. The derivative of the first times this bottom minus the bottom, the derivative of the bottom times the top. So that's S d L over dl, because I'm doing it with dl. Those things go away, and it's all over L squared. So those things go away, and I wind up with negative 36 ds over dl times L minus S over L squared. Okay, now, I know that ds over dl is... Okay, and then I have my ratio. So I've got ds over dl, and I know that that is... I actually don't care. Well, actually I do care because the magnitude is going to matter there. ds over dl is negative 1 over 4. So I'm going to have negative 36 times negative 1 over 4 times, what was L? Do positive. The L is positive, so the bottom doesn't matter. And then the top here, the L, S is L over 4. Okay, so I'm going to have L minus... Oh, I do have an L. Where's my L? L is 500. Minus 125. And the point is that this is going to be... This dominates the equation, right? This is going to be 9 times 500. This is greater than 0. So I minimized. Okay? So you can do first derivative test. You can do the second derivative test. But it's not just as slick as making my little endpoint argument. Okay. So that was totally distracting and did not and denied the beauty of the thing. So let's go back to this. The beauty of the thing, coming back here, now that I spent all that time on the first and second derivative tests, the endpoints are L, so I found the minimum. Okay, so I say that. But more interesting, so I've got everything I want, or I mean I can, right? Because now I just sub into what I've got. So the cost, the total cost, C equals, what was it? 9L plus 36S. So I've got 9 times 500 plus 32 times 125. Which equals, when I plug it in to my nice little calculator, 9 times 500, and I'm going to wind up with 4,500 plus 4,500, which is going to equal 9,000. Okay, so 1 to 5, ignoring all the stuff in the middle about the first and the second derivative tests, which are confusing, because the beauty of this is just using the argument. How do we feel about this 1 to 5? Now that I've kind of, I kind of went off on this tangent that, I didn't mean to. But, and it wasn't your fault. You asked a question and I misunderstood the question. So that's the trick. The whole trick here is to simply plug it in. I mean, it's to simply take the derivative of everything and set it equal to 0. And then solve it and then make an endpoint argument. Now, I can have things that are more complicated. So the box problems, you can do this trick. What did I write? Yes. Which, of course, begs the question, how did I get the right number? Well, I knew if this one was 4,500, that one would be 4,500. Because these are... because 1/2 and 1/2 are equal to each other. So the exponents were equal. That's how I knew it would be that. Okay. Well, that's cool. But this also lets me quickly solve for an expansion path, right? So just a reminder, the expansion path idea was that I have output as a function of cost. So expansion path. Now, note that I don't have to do all that work again. I don't have to minimize with my abstract C, right? I come up here and I grab my ratio. So S is going to equal L over 4 as before. Now I just sub into my two equations. So the Q equaled L to the 1/2, S to the 1/2, which implies, right, I sub this in, that Q equals L to the 1/2, L to the 1/2 over 2, which equals L over 2. That's nice. I got L over 2. Okay. And then I have my other one. C equals 9 times L plus 36 times S. And I plug that in again, and I get C equals 9 times L plus 36 over 36L over 4, which equals, this is going to be 9, so that's going to be 18L. Okay? So now I take this equation here. I'm going to solve this. So that means here that C equals... No, I don't want C there. I want L equals C over 18. So I'm going to get Q, and then I sub this. So I take this equation and combine them. That does not look like a good arrow. That looks like a much better arrow. So I'm going to take these two equations and I'm going to combine them. And what do I get here? And this is kind of cool. Q equals C over 18 over 2, otherwise known as C over 36. Yeah. So how do we feel about that, 1 to 5? So what I did, remember the expansion path. I want Q as a function of C. Okay? So that was the point of solving for that expansion path. So let's go back to the problem set. Okay? Here, what I wanted to solve for the expansion path, right? I wanted this area in terms of quantity. Okay? Let's do that this way. So this is the other way. Okay? So here I had A equaled W times L. And I've got C equaled 40L. It was 40L, right? Yes, plus 30W. Okay? Now I'm just going to take the derivative of both and set them equal to 0. So dA over dL, I'll let L drive, equals, this is a nice little product rule. So I would have d over dL of W times L plus W times d over dL of L. Well, that one's going to be 1. That one's just going to be dL over W. So I get L times dW over dL plus W. And I'm setting it equal to 0. And then I get, from this, I get that dW over dL equals negative W over L. Okay. And now I'm going to solve for my constant. So DC, I'm sorry, my cost. So DC over dL equals 40 plus 30 dW over dL, which gives me that dW over dL equals, and d, this is going to go over here, so this is going to go on top, negative 4 over 3. So I combine these two, and I get, here I'm going to get dW, I'm going to let dW be that, I'm going to get negative W over L equals negative 4 over 3, which implies that I get W over L equals 4 over 3. So there's my optimal ratio. Now I sub back in. I've got A equals W times L. So this means that W equals 4/3 L. So now I get that this is going to be 4 over 3 L times L, which equals 4 over 3 L squared. All right, so for my cost, I get that this is 40 times 4/3, no, 40L plus 30 times 4/3L, which equals, this is going to be 40L, this is going to be 40L, that equals 80L. Okay, so I sub these two into each other, which implies that 80, that L equals C over 80. So now I sub these back into each other, and I get A equals 4/3 C squared, and this 80 squared. That's not a nice number. So that's going to be C squared over 3 times 20 times 80. And someone want to throw that into a calculator for me? So I get 3 times 20 times 80. And that's going to be C squared over 4,800. Which is what I got right there. But I got there, the math was about the same for this one. If I had been trying to minimize costs, this would have been a lot faster. Okay, so how do we feel about that 1 to 5? Okay. So the big other technique, the other way of doing it was to do something like this. Not this, sorry, that's the expansion path. That's a totally kind of different type of thing. This was the way to solve for the problem, right? So what did I do? I took the derivative of everything and set it equal to 0. I solved for ds over dl. So the method 2. All right, we'll write it down here. Method 2. Okay, so take derivative implicitly of both equations. Solve for, I'm just going to put ds over dl here, whatever you're doing, right? Solve for that ratio. Oh, and set equal to 0. Set both equal to 0. Solve for the derivative term. ds over dl in this case. Okay. Sub to find r in terms of L when optimized. I don't like any of this stuff here. Right. So I want to sub for R when optimized, to find that when optimized. And then I want to solve for R, and then I want to plug back into the fixed equation. Make a endpoint. Okay, so someone's asking me, what do I recommend when seeing these types of problems? And my answer is, it depends. One, are you comfortable with, if you're comfortable with doing the implicit, this is faster, okay? And there's fewer places to screw up the algebra, okay? Especially when you're minimizing, okay? when you're minimizing the algebra, those exponents get like, no, okay? So if you've got something where you're minimizing, right, where the thing you're going after has all these pluses in it, it's much faster to just to go after it by just taking the derivative of everything and setting it equal to 0. Okay? So if you're comfortable with implicit differentiation and your chain rule and everything, this is better. What's the other major advantage of this is if you get your formulas but you mess up your setup, you sub later. Okay? So this could be called here derive first, sub later. So if you mess up your setup, you're going to get more points from this kind of derive first, sub later idea. Does that make sense? Now, the other method is easier to understand. Kind of conceptually, the other method is kind of easier. And if you're having trouble with this, go for the other method. It will work. Okay? The algebra will be a little bit less mess. The algebra will be a little bit more messy. But conceptually, that one's kind of an easier type of thing to do. But again, this is kind of derive first, sub later. So if you're confused by a setup or something, but you've got equations that you can take derivatives of, doing this tends to get you more points because the thing that you've messed up, your sub, comes at the very end. If that makes sense. Whereas, and at this point you should be, if you're really good, if you're comfortable with implicit differentiation, picking something to drive, this will get you more of the answer, if that makes sense. So if you're doing it at a test. Now, if you're going on to Calc 3, I would learn this method because this directly ties into using Lagrange multipliers when you get into Calc 3. Okay, because that's how you do these things in Calc 3, period. When you've got lots and lots and lots of different variables to optimize over. So these are nice. All right, are there any other questions? That's a good question. Okay. Now, let's talk about this expansion path, the second derivative idea. Okay. And so I just want to begin. If you want to, you can also do it like on the quiz we took today. You could have solved it using this method as well. Okay. Here I actually did the second derivative test. Oh, the second derivative was really easy. Yeah, on this one you were minimizing, you were maximizing stuff, so the second derivative test is really easy if you're maximizing stuff. Okay. So here I did the same thing here, which is why I did the optimized, and I wind up with the two ratios are negative W over L equals negative 3 over 2. So I wind up with L equals 2/3 W. All right. And then what I did, and I did the first derivative test as well. I had my endpoints here, implying that L equaled that and W equaled that. So I did the same kind of combined thing. Now, again, on the maximization problems, it's not that big of a time saver. Although it is kind of nice because it's the same process for both. On the minimization problems, these things can really be a time saver. Because you've got those long things with adding, and you wind up with these equations that are just huge and huge and huge, with lots of places to mistake. So it lets you turn a minimization into a maximization in one sense. Right? You get the nice derivatives that come out from doing the maximization problem. So if it says minimize, this is like beyond better. But again, for maximize, it doesn't really save you a lot of time. Okay, now let's look at this expansion path. This is interesting. Look at the expansion path. Here, I've got Q equals 36 C over 36. So dq over dc in this case is going to be 1 over 36, which is greater than 0. Okay? So this means that the marginal cost the marginal output for another dollar. This means it cost me $36 to get another unit of output. And notice that this is constant. This thing has constant marginal cost. It doesn't matter how much I produce. Okay? And that's interesting. All right, our constant marginal output or constant marginal cost. Right? So if I do dq over here, I get constant returns to scale. So it doesn't matter how much I output, it always costs me the same. Now, let's compare that situation to Thanksgiving dinner. Okay? So this is different than Thanksgiving dinner. So the intuition behind Thanksgiving dinner. Okay? I have diminishing marginal costs. Okay? So what do I mean by that? Well, okay. It's just me going for Thanksgiving dinner. All right? So people, total cost, marginal cost. All right? So somebody give me, let's say I'm doing something like the square root of, let's see, Desmos. So let's say I've got my cost is the square root of people will give me what? So I want the square root of x times, let's see, if I do 20 plus 1, so the first person, the second person would cost me $6. No, I want more than that. Okay, so the first person, I want more than that. You can't see what I'm doing here. So what I'm doing here is I'm trying to figure out a reasonable cost function for Thanksgiving dinner. Okay? So this is 20 people. I'm going to have to give big numbers here. And then I want to shrink this down. Let's make this, I bet 9,000 or 10,000 would do it for me. Nope, one more. There we go. Okay, so let's say that my marginal cost, this is going to be my marginal cost for Thanksgiving dinner, realistic values. Check out how realistic values these are. Okay, so let's think of, so it cost me, my cost for Thanksgiving dinner is the square root of 10, 1, 2, 3, 4, 10 to the fourth times x, where x is the number of people. Okay? So how do we feel about this idea of what I'm doing, 1 to 5? This is my Thanksgiving dinner cost function. Okay? So if I only have one person for Thanksgiving, let's make it even bigger. Let's make it cost $200 for the first person. So $200 for the first person is going to be like 40 here. There we go. So I'm going to put a 4. 4 times 10 to the 4th. So when I pull that out, it's going to be 2. And then I've got 1, 2, 3, 4 zeros. So it's going to be 2 times 10 squared times the square root of x. Okay, where x is the number of people. Okay, so what does this function mean here? The first person, right, for Thanksgiving dinner. If I'm cooking Thanksgiving only for myself, I'm a loser. And I'm the only person coming to my Thanksgiving dinner, right? So the first person that comes to Thanksgiving dinner, me, my loser self, is going to cost $200. Okay? So my marginal cost is $200 because it's, from 0. My total cost is $200 and the loser is just me. So I'm going to order out some nice Uber Eats or, Grubhub, and I'm going to get some, nice bottles of wine, and I'm going to drink a whole bunch of it. Now, if I get 2 people, however, my cost is $282.84. So the marginal cost of adding another person is only $82.84. Right? So now me and my ex-fiance, who say she broke up with her current person, decided to go to dinner together. And because, we're both lonely for Thanksgiving. So we got, we went out to dinner. We got some Grubhub, I guess, because, the pandemic. But we're talking. We're going to watch a movie. We didn't quite, go through 3 bottles of wine. It's my ex, so I don't exactly want to. I don't need to spend a lot of money on her. Type of thing. So it costs a little bit. The cost is greater, right? It's costing us more money, $282.84. But the cost of adding her onto the meal is only $82.84. Now, let's say we have 3 people, okay? So I'm going out with my mom and, and all that. I'm going out with my mother and my, my brother. My mother and my brother and I are going out for dinner. We might cook at home. The total cost is going to be, we're going to make some casseroles and stuff. We'll probably have a lot of leftovers. $346.41. So this is for 3 people. Now, what's the cost at the margin? How much did that one extra person cost us? Well, I've got 346.41 minus the old one, which was 282.84. So the cost at the margin for the third person is $63.57. Okay? How do we feel about that 1 to 5? Okay? Now, let's go here. Let's say I've got, a lot of people coming for Thanksgiving. I've got 10 people coming for Thanksgiving. The total cost for 10 people to come to Thanksgiving dinner is $632.46. All right, so $632 and 46 cents. I'm not going to work out what the marginal, well, I can. But now the 11th person. The 11th person is right here. For 11 people, it only costs $663.32. What was it, 32 cents? Yeah, 33 cents. So now when I subtract those two numbers, so if I'm already feeding 10 people, what does it cost me to feed an 11th person? That's wrong, because there should be a 6 there. So it'd be 663,632. Yes. Okay. So it only cost me, the marginal cost at 11 people is $30.87. Okay. So if I invite my whole family, right, and then my cousin shows up with his latest fling, I run downstairs to the basement, grab another box of wine, and that's all it really cost me to add him to the dinner. My cousin's date. All right. Any questions about that? Does that make sense? 1 to 5. How do we feel about that? So that's what this graph is saying. It always costs me something to feed more people, right? If I have more people show up, it's going to cost me more money. But the amount of money it costs, the amount of additional money that it costs per person goes down as I feed more and more people, right? If I'm feeding 100 people already, the cost of adding one more person to that buffet is $9. Okay? If I'm already feeding 100 people. This is called diminishing marginal cost. And that's what happens with Thanksgiving dinner. And that's also what's happening to that area problem. D squared C over D, this should be squared. I'm sorry. Right, so this right here is going to have a negative second derivative. That means it costs me less and less money to add each additional person. And that's kind of the point of that second derivative stuff. As I see it, as kind of a real world application of this concavity condition. Okay? All right. So tonight what we talked about was, we talked about this other way that you could find stuff, right? You can do optimization problems simply by taking the derivative of everything implicitly and setting it to 0. And then again, I said make endpoints arguments. It's much easier. And then what you get is this minimum. And especially for the min problems, the minimize the cost problems, this is usually faster. Now you can wind up in situations where you're going to have like those box problems. You can wind up in algebra death no matter what you do. But if it says minimize the cost, this is a good way to try it. And then we talked about this idea that I can solve for an expansion path that will give me the cost per quantity, or the quantity per the money per output. And then I talked about like constant marginal returns, constant returns to scale. This idea that here I've got a marginal cost of that, and then I've got this constant thing, and then I want to think about what it means to be concave in terms of Thanksgiving dinner. So this is concavity in terms of Thanksgiving dinner. All right, so the plan for, reminder that the test is on Saturday. There are more. This is the last kind of thing. There's no class on Wednesday, but I will have office hours. And if you guys want, I could go over to the problem set online if you want to during class time. But there's no required class. If you want me to go through the problem set, I'll be happy to. Some more of those optimization problems. And then Wednesday we'll have office hours. Even though it's a holiday, I'll still hold office hours. And then on Thursday, it's Thursday evening. No, when's the other test review? No, Thursday during the afternoon is a test review. Friday at 3 p.m. is a test review. I have extended office hours on Friday. Test is on Saturday. If Ada does something, it's just lounging around right now in the Gulf. Nobody knows what it's going to do. If the university closes, we will move the test. But right now, it's looking like we'll only do it if the university closes. Are there any other questions? Okay, well, that's it for me. And I will post another video. I might make it tomorrow. I might make it Wednesday. On the people were asking for nothing else matters in terms of the exponential and the log. Okay. I'll hang out in Discord if you want to ask questions. And you can ask me stuff there. Good night.